Hi. All right, here we're going to go ahead. We're going to take a look at universal gravitation, problem 7. That one involves Halley's Comet. So it says, Comet Halley approaches the sun to within 0.57 AUs, and its orbital period is 75.6 years. They give you the value for an AU, and they say, how far from the sun will Halley's Comet travel before it starts its return journey? And they give you actually like a really nice diagram to help you figure out how to do it. So the sketch they give you looks like this. Like, hey, there's our elliptical orbit, and here's the sun at the near focal point, right? And they tell you that at the near point, so that's at paraapsis, they tell you that this distance here to the sun is 0.57 AU, and they want to know the distance to the far point, to apoapsis. Here, that's what we're trying to find. They call it x. And they point out to you that this is 2a. All right, you're like, what the heck is that 2a? That's about the equation for an ellipse, and actually how it all plays into Kepler's third law of planetary motion. So I'm going to really quick run through Kepler's third law of planetary motion for you, and then talk about that. So if I analyze Kepler's third law for a circular orbit, okay, and then I'm going to kind of talk about how you modify it for an ellipse. But for a circular orbit, basically you've got something going around in a circle, right? There's my object in the center, like the sun in the center, and you say, hey, if I have a circular orbit and I'm going around this orbit bar, you say the only force acting on that object going around is gravity. And so if I do the circular motion calculation, it looks like this. Some of the forces in the radial axis is mass times acceleration centripetal. That's going to be the mass of the thing going around in a circle times v squared over r. The force is gravity, so that's going to be big G, the mass of the sun, mass of the thing going around the circle, over that distance, the radius of the orbit squared. That distance between the radius of the orbit and a circular orbit. And so if I tidy this up, we say the mass of the thing going around the circle drops out. Kepler's third law has to do with the relationship between the period of the orbit, the time to go around, and the radius of the orbit. So to get the period in the equation, where it says v, I'm going to substitute in speed is distance over time. So I look at the distance to go around once, 2 pi r, the circumference, divided by the time to go around once, the period. So that would be 2 pi r over t. Now I'm going to square it in the formula, so it would be 4 pi squared r squared over t squared. Now there's still an r down there. And then over here I got g mass of the sun over r squared. Now I'm going to tidy this up one more time. Let me point out that this r, once again, in the circular motion formula, centripetal acceleration, that is the radius of the circle. And the r here is the distance between the middles of the objects. Those are essentially the same. If the object in the middle is like huge, and the one out here compared to its very small mass, then pretty much it's going to orbit around the center of that object. The center mass is so close to the center of the center object that they're basically the same thing, these two r's. And so that lets us get away with that. So I'm going to move this r squared over here, and I'll have r to the fourth divided by r being r cubed. And so what I'm going to get here, let me rearrange some stuff. So that'll be an r cubed then. I'm going to move, let me go ahead and, There's an r cubed on top. I've got a t squared on the bottom. Okay. And I've got a 4 pi squared, right? I'll just do that for now. G mass of the sun. One last rearranging I'm going to do. I'm going to move the 4 pi squared down. Well, whatever. Let me move the t squared and the GMS there. This is the way you typically see this thing written, so I'm going to write it that way. Okay, so what I want to point out is that for things orbiting the sun, this is constant. For everything orbiting that sun, that mass, that center mass, this is a constant, 4 pi squared g, mass thing in the middle. And so if I've got things doing circular orbits, there's this definite relationship to the radius of the orbit we need and the time it takes to go around. The bigger the radius distance out from the center, the more time it takes to go around. But what I can do with this is I can rearrange this. And move this r cubed here. T squared to r cubed then is equal to this constant. What that means is, if I'm looking at, say, two different objects orbiting the same center, right? Each of them will have their own t and their own r value, but they'll both be that ratio, t squared to r cubed for this guy, and t squared to r cubed for this guy. Say object A, say object B. You say A would be equal to tb squared t over r for b squared. You know, cubed. You know what I'm saying? And so if you know like 3 of those pieces of data, you can solve for the 4th real quick and easy. Okay, just a side note. We're going to do that essentially in this problem. Okay, but there's one last adjustment, and that is this is an ellipse. This was specifically for a circle, right? Now, I'm going to be 100% honest with you. I haven't seen the derivation. Actually, I think I know where I can find it. But I haven't seen actually gone through the derivation for an ellipse for this equation. But what I'm told is that essentially you can take this equation, and where it says r, you can instead swap in for an ellipse half of the length of the major axis, so the semi-major axis. So if you have an ellipse, you can draw a line here. That should really be on that line. Anyway, you have this line that runs through from the near point to the far point, right? And that's the longest distance across that ellipse, and here's the shortest distance across that ellipse. Well, I mean, it's the other axis are perpendicular. So this is the minor axis, the major axis. The length of the major axis is 2a. A is the semi-major axis. And so this r here is actually, you can swap it in for an a. Okay. And the other day I saw someone saying that technically when you do this, this mass here is actually the sum of the mass of the planet orbiting and the thing in the middle, the sum of them. But we're dealing really with cases here where the mass in the middle is huge compared to the mass of the little teeny thing orbiting it, so you can kind of ignore that, just the mass of the thing in the middle. So this is the way that I am used to seeing Kepler's third law of planetary motion written out. And when we do it that way, like I said, for an ellipse, you're just using the semi-major axis. So that's the trick we're going to do here. All right? So in this case, they're telling us that for Halley's Comet, so here we go, we're going to set this up. The period for Halley's Comet squared over that, and then instead of r, we're using the semi-major axis. That's a for Halley's Comet cubed, has got to be equal to, and you say, no wait, that's going to be equal to, let's do something else we know that's going around the sun. Let's use the Earth. Now, so we'll do the period for the Earth squared, because we have that data, and it's actually going to be really nice in this calculation. And those will be equal to each other. But wait, we know that they were really nice, and they gave us the time, right, the period for the Halley's Comet orbit in years. That's kind of handy, because if I'm going to do this ratio and compare these, they have to be in the same units. And so if I use years, well, you know what the time for Earth's orbit is? 1 year. So that turns into just 1 squared on top. And then the distance here, and one distance they gave you to work with here was this 0.57 AUs, right? And that's handy because in AUs, this for the Earth's orbit is 1 AU. In other words, A for Earth is just 1 AU. So this ratio we're going to end up with here is just equal to 1. Handy, huh? If it's in years and AUs, it comes out to equal to 1. That's really nice, okay? So what's this going to be for Halley's Comet? Well, the time we know is 75.6 years. Now that A, though, well, they didn't give us A, right? Our whole goal is to find this. Say like, okay, well, look. I know that this plus this is the thing I'm trying to find, that far point, the distance out to aphelion, or apoapsis, I mean, for Halley's Comet. That's equal to twice the semi-major axis. So I can write a little equation that 2a is 0.57 plus x, right? So what I'm going to do then, if I rearrange this, divide both sides by 2, take that, right, and divide by 2, that's what's going to go in here for a, right? So it'd be 0.57 plus x over a. And now that denominator needs to be cubed, right? That ratio is 1. I can now, uh-oh. Right. What I just do, over two. Yeah, right. Yeah. Okay, A is, okay. That's what I get. And so like, hey, look, that's an equation, just one unknown x. I can solve for x. So rearranging, just move this to the other term, rearrange. So I'm going to get 75.6 squared times 2. No. It's going to be I'm going to do too many math steps at once. I'm moving this over. I'm going to cube the 2 in the bottom. That'll be an 8. So it'll be an 8 in front there. And that's going to be equal to 0.57 plus x cubed, right? So let me go ahead and let me just solve this and then take a cube root. So I'm going to take a cube root of both sides. There we go. And that'll be 0.57 plus x, and then I can subtract 0.57 from that and get x, right? So it's going to be that cube root of 8 times 75.6, right? Minus 0.57. Okay, and that'll be my x in units of AUs, right? So that is the plan. So let's do it. Now, conveniently, I did my math already, and so in my calculator, and what I got was 35.1888. Okay, and so that's the distance in AUs out to apoapsis. Yep. Okay, and so that's problem 7. And so that's a handy thing. Like I said, if this happens to be in year period, and this is in AUs, well, for Earth that ratio is just 1 to 1. So that's really kind of handy. But you can use technically whatever units you want here, squared to cubed and squared to cubed, and it should work. Now, if you want to get answers out in actual, like, obviously in the normal metric units, you use normal metric units. Okay, that's it. Problem 7.